All right, so this begins our lecture video on Unit 2.2, focusing on solutions in particular. So to start off with this section, we have a couple definitions. First of all, what is a solution? A solution is when stuff to us is indicating atoms of compounds, are dissolved in liquid. In biology, this liquid will commonly be water. But in other branches like chemistry, you're probably talking about other types of solutions. So that is the solution. That is both the stuff and the liquid. So that's both the solvent and the solute. The solvent is what does the dissolving. So in the example I just gave, it would be the water. And the solute is what is getting dissolved. And so a good example might be salt. So as you can imagine, you usually would have more solvent than solute in order for that, say, that salt to be dissolved within the water. Now, what's unique about water, and this is actually a definition, so water is a super solvent. Water dissolves the most solutes compared to other solvents. But there's a couple different types of compounds that would need to dissolve, right? So what makes it a super solvent? It's the fact that it can dissolve both covalent and ionic compounds. But there's different ways that each of those compounds will dissolve. So how do covalent compounds dissolve? So the molecules, when a covalent compound dissolves, the molecules will stay intact. So if we have an example, sugar and water, the sugar molecules will stay intact. And in other words, no bonds inside the molecule will be broken. This text is getting a little busy here, so I'm just gonna hold these for distinction. And there's another good simulation for this. Again, from the University of Boulder, similar to the atom building simulation. This is accessible online. If you look up Colorado solute and solvent simulation, it would probably come up. So we'll start with sucrose. Sucrose, in other words, table sugar, and this blue liquid is supposed to represent water. And if we can pause this, you see how when we dump the sugar, we've got this cluster of molecules here. And it hasn't hit the water yet, but what happens when it hits the water and is in theory dissolving, notice that these sugar molecules are still intact. Or in other words, the water is not getting between the carbon, hydrogen, and oxygen here. So they're still maintaining a shape. And that's why when you dissolve sugar in water and you drink the water, say for instance, you would still taste that sugar, that sugary sweet taste. That molecule is not coming apart as soon as it hits the water. So that's how a covalent compound dissolves. Now, how does an ionic compound dissolve? In contrast to the covalent compound, the ionic compound will come apart. And spread out. And the bonds that held the atoms together will be broken by water. And a good example of an ionic compound would be sodium chloride. So if I remove the solute here, go to salt. It's not letting me. No, maybe not. There we go. All right, so here you can see, and you remember if we talked from earlier lectures when we were talking about ionic compounds, it's all those positive and negative charges forming a grid of repeating units. And that's how you get, if you picture a cube in your mind, a cube of sodium and chloride atoms kind of bounded together, and you picture this sort of saline crystal structure. That's what we're looking at here. Now, before it hits the water, it still maintains that grid-like structure, but when it hits the water here, you can see the water is now in between those sodium and chloride ions, and now they're breaking apart and spreading out. So that's the key difference between how covalent compounds and ionic compounds dissolve in water. So in other words, what dissolves in water? Both ionic and covalent compounds dissolve in water. Water has polar covalent bonds, so it can dissolve other stuff or other atoms and molecules with polar covalent bonds. So remember, polar, if something is polar, it means that there is an unequal sharing of electrons. So if you remember in water, the oxygen is more of the electron hog, and it has that net negative pole to it, whereas the hydrogen would have a net positive. That's why it creates that bent-like structure in the molecule. And sugar, because it also has that polar component to it, it also dissolves easily in water. However, how does water end up dissolving things with ionic bonds? So water has small charges. It's got the positive and negative charges, and those can form connections with ionic compounds that also have positive and negative charges. And that's how those ionic compounds end up dissolving. But even though water is a super solvent, there are still some things that do not dissolve in water. And what doesn't dissolve? It would be nonpolar covalent bonds. And so nonpolar is the opposite of polar. Nonpolar means that there's an equal sharing of electrons. So what is an example of something that is nonpolar? That would be something like oils. Or fats. A good example of that would be like, say you're trying to scrub off oil, like the oil has stained your clothes or something like that. If you just put water on the stain, it's not going to get the oil out. It's because the water itself is not able to dissolve that nonpolar compound of the oil. That's why you need to use soap. So soap, which contains fat, right, also has that nonpolar covalent bond component to it. And so that's why the nonpolar is able to dissolve the nonpolar. So like dissolves like. That's a common rule in chemistry. Okay, so now that we've kicked off unit 2.2, that will be the end of this video.